Suppose that we have these two segments, segment AB and segment CD, and then point L is on segment AB, and point M is on segment CD. And with this arrangement, we end up with this proportion. We end up with a proportion that says that AL, I'll rewrite it up here, AL over LB is equal to the ratio of CM over MD. So in other words, when I had L kind of stuck on segment AB and M stuck on segment CD, the way that those two segments were divided up, if I made ratios of those sides of those distances created, of the two parts of this original longer segment and the two parts of this original longer segment, if I made ratios of those, they'd be equal. Now what we say when that happens is that L and M divided segments AB and CD, they have been divided proportionally. And that's a term that we're going to see in a couple different theorems that we're about to look at. So I just want to kind of show you what that means. If I'm going to divide two segments proportionally, it means that if I make a ratio out of the two parts of one segment, it will equal the ratio made out of the two parts of the other segment. Now, Theorem 7.3 is called the triangle proportionality theorem. And here's what it says. If a line that is parallel to one side of a triangle intersects the other two sides, then it divides those sides proportionally. So let's look at this diagram here to kind of understand what this is saying. Let's suppose that segment DE is parallel to segment AB. Then I have a line that is parallel to one side of triangle ABC. DE is parallel to a side of triangle ABC. That line is intersecting the other two sides of the triangle. It's intersecting AC and BC. According to this theorem, it's dividing those proportionally, which means that, so you can see, I'll kind of do some color coding here. You can see that I've taken segment AC and I've divided it into this part here and this part here. And I've taken segment BC and divided it into this part here and this part right here. Now what we just learned by Theorem 7-3 is that if I take DC and AD and make a ratio out of them, it will equal CE over BE. CD over AD will equal CE over BE. But there's more to this one. This is what I want to show you. By taking this and doing some rearranging and some other tricks with it, there's a couple other proportions that will come out of this. One of them is that I can take CD. Let's see, I'm doing a couple proportions here, so I'm just going to kind of set up my proportions in white. I can take CD and pair it up with CE, CD and CE. That ratio will equal DA paired with EB. So you can see in this first proportion, I took the two segment lengths that are kind of on the left side of this triangle, CD and DA, put them together along with the two segment lengths that are on the right side. On this proportion, I took the two segment lengths that are kind of on the top and paired them with the ones that are on the bottom, CD and CE, paired with set equal to DA and EB. The other thing that I can do, and I guess there's two more, so let me actually make another proportion here that I'm going to fill in. I can take CD and I can pair it with CA, and I guess maybe I need another color for CA, so let me just kind of color that in there. Pair CD with CA, and it will equal CE paired with CB. Give that a color right there. CE will get paired with CB. So I took the top part over the whole thing would equal the top part on the right side over the whole right side of my triangle here. And now I can do the same thing with the bottom part and the entire left side. So AD would equal, or AD over AC or CA would equal EB over the entire left side, CB. And of course, each one of these I could also flip-flop, I could also kind of turn upside down, and that would still be true. So from this one theorem and this diagram, we could get these four proportions that would all be true. Now let's take a look at another similar diagram and see if we can fill in, if we can complete each one of these proportions. For the first one, we have A over J equals C over blank. Well, the A over J is like the top part over the entire right side, the top right over the entire right side, equals the top left over, and it would make sense if we're going to be consistent here. If I went top right, entire right, it would be top left, entire left, which would be K. So I'd have a K right there. Part B is A over C equals J over what? Well, how would I be consistent there? If I went A over C, top left over top right, equals entire left over, it would be entire right. That would be a K right there. Part C is B over J equals D over, well, this is K again. I didn't mean to do that with all these answers being K, but it's just the way it turned out. Then we have A over B equals C over, that would be a D, right? Top over bottom equals top over bottom. And I have A over C equals B over what? So top left over top right equals bottom left over bottom right. So that would be a D. B over D, so bottom left over bottom right, would equal entire left, which is J, over entire right, which would be K again. In example 2, it says, in this diagram, first of all, notice in this diagram I have a segment that's parallel to one of the sides of my bigger triangle here. So I know that theorem 7-3 will apply in this situation. It says if CE equals 3, so that's a 3, and EB equals 6, and DE equals 3.5, then what will AB equal? Okay, well, what we have going on here is we have this segment that's parallel to one side of the triangle. Now that tells me that it's going to divide CD, it's going to create a proportion that says that in this picture we would know that CD over EC would equal CA over CB. Now why did I pick that particular proportion out for this picture? Well, CD over EC equaling CA over CB, and of course I knew that again from theorem 7-3 that I just learned on the previous slide. That proportion compared with the fact that angle C would be congruent to itself tells me that this small triangle is similar to this bigger triangle by side angle side. Right? And I have side angle side similarity based using this proportion and this angle congruent to itself. And that would mean then that the third side of the triangle, right, DE and AB, the third side of those two triangles, they would also be in the same ratio as these guys here. So if I have an X that I'm trying to find right here, then what I can do is I can use the fact that now I know that we'll say DE over AB would equal CD over CA, and it would also equal EC over CB, right? Every one of these ratios that I set up here is a pair of corresponding sides between the little triangle and the big triangle in this picture. And I know that those two triangles are similar, so I know that all those ratios of corresponding sides should be equal to each other. Now, if I'm trying to find AB, if I take this ratio here, and I put an X where the AB is, and I put a 3.5 right there, now I just need to fill in another ratio using one of these and the numbers from the picture. Now, of course, I don't know anything about CD and AC, so that's probably not the one I'm going to concentrate on right there. But if I look at EC over CB, I know both of those lengths. I know that EC is 3, and I know that CB would be 9. It'd be 6 plus 3. So now you can see I have a proportion set up that I should be able to solve. I know that 3 times x would equal 9 times 3.5. 9 times 3.5 would be 31.5. And that tells me then that x would equal 31.5 divided by 3, which is 10.5. So the length of AB is 10.5 in that picture. Again, that came from using theorem 7-3 to determine that these two triangles were similar, triangle CDE and CAB. And then based on that similarity, I could set up all of these ratios that should be equal because they're ratios of corresponding sides. Now if I look at part B down here, I've got different values. So I'm going to erase these real quick so I can use different values. Oh, I forgot. Oh, let's just erase that. Sorry. Okay, so CA is equal to 12. CA is equal to 12. So this entire thing here is a 12. DA is an 8. CE is 6. And we want to know, what is CB going to be equal to? Well, this looks like it's something like theorem 7-3 pointed out, right? First of all, I notice that if this is 12 for the whole side and this part's 8, I can fill in a 4 right there. All right? And I know that if I take DC and put it in a ratio with EC, DC and EC paired up should equal AC over BC. That would be one of the proportions that I can set up based on theorem 7-3. So DC over EC equals AC over BC. Now if I fill in numbers or variables in some cases for these things, let's see what that looks like. That would be a 4 over 12 equals AC, oops, sorry, I did that wrong. It'd be 4 over 6, EC is 6, equals AC, which is 12, over BC, which is an X. Cross multiply here, and I get 4x equals 6 times 12, which is 72. Divide both sides by 4, and x equals, let's see, 72 divided by 4 is 18. So x equals 18, so the length of CB is 18 here. Now we have a corollary to that original theorem that we learned at the beginning of this video. It says that if 3 parallel lines intersect 2 transversals, then they divide the transversals proportionally. So in this picture, what does that mean? Well, you can see I have my 3 parallel lines intersecting these 2 transversals. That tells me that LN and QR have been divided proportionally. So LM over MN would equal QP over PR in this picture. So how can we use that? Well, if I look here, I have a similar diagram. I have some values for A, B, and C, and I need to find some other things. So I know that in this picture, with these lines being parallel and these two things being transversals, I know that A over B would equal C over D. So if I fill in these numbers here for these different variables, I'd have 2 over 3 equals 5 over D. Cross multiply, I get 2D equals 15. Divide both sides by 2, and D equals 7.5. Now in this problem, I know the same general formula will hold true. A over B equals C over D. Now A is 4, and B is 8, and C is 5, and it wants me to know what C plus D is. Well, let's just figure out what D is going to be equal to here. I'd have 4D equals 8 times 5, which is 40, which means that D would be equal to 10. So C plus D would be 5 plus 10, which is 15. The other way I could have set that up is I could have said, I could have went 4 over 12, because that's A over A plus B, equals C, which is 5, over C plus D. I'll just put a Y there. And then I would have had 4y equals 60 and y equals 15. So again, I would have got the same answer. The last theorem we're going to take a look at on this video is called the triangle angle bisector theorem. And it says that if a ray bisects an angle of a triangle, then it divides the opposite side into segments proportional to the other two sides of the triangle. Or in other words, if I look at this diagram, if the measure of angle 1 equals the measure of angle 2, in other words, angle ABC has been bisected, angle 1 and angle 2 are equal, then I have segment AD and DC that are proportional to AB and BC. Or in other words, if I'd say AD over DC, it would equal AB over BC. The two parts of the opposite side from this angle, here's the angle that got bisected, here's the opposite side. Its two parts that were created by this bisector right here are going to be proportional to the other two sides of the triangle. So if I look at example 4 here, I've got this angle that got bisected. Angle ABC was bisected by segment BD. You can see it created two smaller congruent angles. I got AB as a length of 12, BC as a length of 24, AD has a length of 10, and I want to know what is this entire length there. Well, what I can do here is I can maybe put an x right there, because I can set up a proportion that says 10 over x would equal 12 over 24, right? Based on this theorem that we just learned. 10 over x would equal 12 over 24. Cross multiplying that gives me 12x equals 240. Dividing both sides by 12 tells me that x equals 20. So if this right here is 20, but I really want to find AC, I know that AC is going to be AD plus DC. So it's going to be it's going to be 10 plus 20. So AC will equal 30.